Hi, I wanted to talk about RSA encryption. RSA encryption is, uh, let's get to the next slide. And I'm going to be going over what it is, how to work with RSA encryption, and what the algorithm looks like in particular. And my code is going to demo what an RSA encryption looks like in its main function, and then I'm going to walk you through the code as well. All right, so what is this used for? So RSA encryption is used for the real world today. And um, it's specifically used for transmission, so like Bluetooth and Wi-Fi, messages in general, and so forth. Um, and it uses like a key and then a lock to these different sets. I'm going to be going over more of that in the next slide, but it has something called a public key and then a private key. It encrypts the text that is sent through, and then it sends a private key and decrypts that to your device. Otherwise, you'd have messages floating around that are uh, something called clear text, where you would be able to, a hacker would just be able to take the message um, and and read exactly what it says, exposing private info. So the public and the private key are what encrypts it and decrypts it. So how does the algorithm work? So it implements something called the extended Euclidean algorithm. So Euclidean should be a little bit familiar with you guys listening. It should um, Euclidean means that it's like geometric, or it has it works with shapes, um, just as you would have like in seventh grade or something like that. So geometry is a big part of it, and we're we algorithms you can look at as almost like a network of certain things. In the first slide, you kind of saw like a network mesh. That network mesh was is representative of like nodes and those communication to those nodes. But what it does is it implements that extended Euclidean algorithm, and then to find the greatest common divisor of two numbers, a and b, along with the coefficient x and y. So ax plus by equals the greatest common denominator of a and b. This is used in RSA to find the modular multiplicative inverse. Um, and after that, it will the modular exponentation calculates x to the y mod n in a very efficient way using square and multiply technique. And then it generates the private key um, with the private like key d, which we'll see later. The equation isn't up here. I should have put it up here. But from the given number, prime numbers p and q, and the public exponent e, which is used for the decryption. Um, so let's go over the worst case and the best case scenario. So the worst case is 0 log n, and the best case is omega log n. And the biggest question that I had when I first saw this, and we did go over this in our class as well, is why are they the same? Um, so the worst and best case scenarios for RSA encryption are the same because of the time complexity, which is that, I mean, this is the time complexity O log n and omega log n. But it's primarily determined by the modular experimentation step, which is the time complexity of O or omega log n, where n is the modulus. Um, In RSA, the encryption and decryption operations involve raising a number to a large exponent modulation or module of another number, the modulus. The modular experimentation step is typically performed using the square and multiply algorithm, which has a time complexity of omega log n, which is because the number of multiplication required to compute x to the y mod n is proportional to the number of bits in the binary representation of y, which is log 2y. As a result of both of that, the worst and best case time complexities or scenarios for this are the same because they're just log of n. Okay, so now we're going to go on to the code. And I wanted to use this online just because the .NET 7 and 8 compiler for C Sharp, we're having a little bit of a hard time working on the laptop that I got that was new. But so first we're going to use system and then system.numerics. In the original file that I have, it would also use the namespace, but because there isn't a folder and it's not compiling with a list of other C# files, we're just going to use both of those, using system and then using system.numerics. So the big part of it is first, if you'll notice, we use Euclid right here, the Euclid method. So the method calculates the greatest common divisor of two big integers, a and b. And then it returns a tuple containing the greatest common denominator and the coefficient x and y such that a times x plus b times y equals the greatest common denominator of a and b, which we kind of went over uh, that equation in how it works and one of those PowerPoint slides. So modular ex the modular experimentation with big integer x, y, and n. What that does is it calculates x to the y mod n using a recursive approach. So you recurse until you use y equals 0. Until we get that, we're going to keep running variable z as as this right here. So it keeps looping until we run out where we get y equals 0. The generate private key method, what we have down here, and this is what I was going to talk about later, is just n equals p times q. So once those two prime numbers, p and q, it once it determines that those are, well, it should be a prime number if I remember right. N equals p times q. Then we have big integer phi equals p minus 1 times q minus 1. And we get that to get phi, and then we get the multiplicative inverse of e mod phi. Once we get that, we'll return, that's what's returned by d. And the encrypt method and decrypt should just call the other methods. So yeah, as you can see, encrypt and then decrypt use modular experimentation. Here, this one right here. And it calculates the value, big integer e, and then big integer n. which if you can tell at this point too, this is why the worst case and the best case um, of big O notation are the exact same because they're using the same method, especially for, I mean, this algorithm that I have. I think that it would be mostly the same in others as well. But here's what I do to test this out. So I'll do big integer p equals 63, big integer q equals 53, big integer e equals 17, and then big integer n equals p times q, which is the modulus. So if you get big integer d equals generate private key, p, q, and e, and then we write the line public key en, and we get those values with the correct brackets right here. And then we'll get the message, the encrypted, and the decrypted right here. So we should, if everything is correct, we should get this as the same value. So original message should be right here, or encrypted should give a different value, and then decrypt should give us the same value. Since this is a public compiler, it just has the first thing up as hello world, but let's try to run this and see what it gives us. Right, so as we can see, it gave us these correct ones. That one should have been obvious unless something terrible is going on. But the original message is 42. Encrypted, it's going to be 2557. And then the encrypted message or decrypted message is 42, which is the original message. So this all worked out correctly. But yeah, this is what it will look like. And although this is simplified, you will see more complicated with encryption and decryption. This is a large part of our world, and I was glad to see how it worked and share that with you. Thanks for watching.